So let's talk about FIR filter design using windowing. FIR filter design using windowing methods. Using windowing methods. So what the basic funda behind this is that we have think about a system. Think about like a low pass filter. Okay, the low pass filter frequency response is going to be ideal. Low pass filter is going to be, the amplitude is going to be 1. Okay, and it's going to pass some frequencies from minus omega c to omega c, right? And this is going to be like the cutoff is going to be like, this is going to be 2 pi. So let's say this is a normalized frequency, this is normalized frequency, and this is 2 pi. Or just one second. So so this will be pi. Sorry, yeah. So this will be pi. So from minus pi to pi, this is how it's going to look like, the frequency response, and it's going to repeat every 2 pi, right? So it's going to be like from 2 pi minus omega c to 2 pi plus omega c. It's going to repeat. So this is your ideal frequency response going to be. Now if I take a IDFT of this guy, or IDTFT, okay, IDTFT, inverse discrete time Fourier transform of this guy, it's going to give me a sinc function, right? It's going to be like something like this. It's going to be centered around zero. Okay, it's going to have a maximum amplitude, and it's going to dip down now towards the lower amplitudes, and it's going to be like from minus infinity to infinity. So it's going to have this values at 1, 2, and this is going to be at multiples of pi. So depending on the omega c, you will get a value at this particular point, it will be a 0. Okay, so this is a sinc function which you get output. So if you look at this sinc function, you see that sinc function, you see that it is first of all from minus infinity to infinity. So that makes it non-causal. Okay, it's basically a non-causal system. So and if you see the length of this system, it's infinite, right? It's infinite. Okay, so there are two things: non-causal because you have non-zero values of this particular h of n. H of n has got non-zero values for values of, that is h of n is non-zero for n less than 0. So that makes it non-causal. Okay, and second thing, if you see h of n is has a infinite length, so that makes it infinite, a filter with infinite. So I mean yeah, so it gets converted into a IR form, right? So, infinite impulse response form. Now so we know that first of all, when you make a filter non-causal, implementation is an issue. Okay, so this kind of filter is not implementable, and second thing is this is infinite, so we are basically dealing with finite impulse responses. So we got to convert somehow. What we got to do is we got to actually truncate this negative side. Okay, that is, you have to forcibly make it 0. And secondly, what we have to do is we have to convert this from 0 to, what we will be left with is a sequence from 0 to infinity. That sequence again has to be truncated. So all the parts outside a certain length m has to be converted to 0, right? So that's the whole idea. Like you need an ideal filter first of all, but that ideal filter, the IDTFT of that ideal filter, the frequency response, okay, the IDTFT of the frequency response is infinite and it's non-causal. Okay, we are dealing with FIR filters right now, so we want the length to be finite, first condition, and second thing is it has to be a causal system. So what you will do is you are going to forcibly make the values of h of n, which is for which n is less than 0, right? H of n for n less than 0 to be 0, and we are going to truncate this sequence on the positive side too. So whatever we'll fix up a length m, okay, and any value outside this m has to be converted to 0. So so h of n, which is from minus infinity to infinity, has to be brought down from 0 to m minus 1. This from minus infinity to infinity, it has to be brought down to having a non-zero values, from 0 to m minus 1, and it should be 0 outside this interval. Okay, so that's the whole idea. So what you are going to do is, so first thing, let's see what are the effects, how we are going to do that. Well, you can do that like think about a simple rectangular window. Okay, we'll just take this example right now. Think about a rectangular window which is having, let's say, w of n is 1 from 0 less than equal to n less than equal to m minus 1, and it is 0 otherwise. Okay, so otherwise, right? So what if I take this window function? This window function is so let's go back to this example, h of e raised to j omega. Let me just copy this. Let me just first copy this thing. Okay, let me just redraw only. So you have this guy here, which is this is the frequency response from omega c to minus omega c, h of e raised to j omega. Okay, so this is your, and this is in this is periodic into pi. So this IDTFT of this particular frequency response turns out to be a sinc function, which is something like this, right? Okay, so it's going to go on till this way. It's going to be a dipping function, like it's going to go till to 0. Okay, a damped function. It's going to go till 0 as it moves towards infinity, as your time period goes towards infinity. Okay, from minus infinity to infinity. Now this guy has to be truncated to from 0 to m, 0 to, let's say, m. What I am going to do is I am going to take a simple rectangular window, one of the window. Okay, this is not the only window. I'm just using a simple case right now. I'll use a rectangular window, which is a window which has got values from 0, 1, 2 till m minus 1. Okay, the amplitudes are 1. I'm going to use this window, and these are all zeros, and multiply the two. Whatever I get here, h of n, I'll multiply this with w of n, and I'll get my new frequency response, impulse response, sorry. So hd of n will be h of n into w of n. So now what is going to happen is, the moment I multiply this, my hd of n will be not equal to 0 for n from less than equal to 0 less than equal to m minus 1, and it will be 0 otherwise, right? Because I am doing a one-to-one multiplication here. hd of 0 is h of 0 into w of 0, hd of 1 is h of 1 into w of 1, and so on, till hd of m minus 1 is h of m minus 1 into w of m minus 1. So outside this interval, w of n will be 0, so naturally this hd of n will go to 0 outside that interval. So now what I have done is, I converted a non-causal function, non-causal infinite h of n into a finite hd of n. So this is going to be my the impulse response of the designed filter. See, we started off with like a desired frequency response. Again, in a FIR filter, we always look at like what is the desired frequency response we want. Okay, then using this desired, this is what so let's say our application is there. I want to design something which is a linear phase. Okay, and then this desired frequency response, I take a IDTFT of that. Naturally it is going to be a non-causal function. Okay, think about like this is a low pass filter, ideal low pass filter. It will turn into a sinc function because rectangular curve in one domain turns out to be a sinc in the time domain, right, or the vice versa. So then this is a non-causal infinite, and then what I do is I truncate this sequence into from 0 to m minus 1 by multiplying it as a window function. Now the effect of this particular process is that what happens is, first of all, these flat lines turn into something like you get some kind of a ripples. Okay, this is the first effect. You get ripples. You won't get a flat response. Okay. Second thing, you will get some kind of a transition band. It's not going to be a flat slope transition band. Okay, it's going to have some kind of a slope in that. It's here in this case, right? It's a flat drop from pass band to the stop band. Okay, it's not going to be the story now. You will have some kind of a transition band which will come into picture, and then you will also get some kind of a ripples in this stop band. Okay, you are going to get some kind of a ripples in the stop band. So these are the after effects of converting a non-causal infinite sequence into a finite causal sequence, because you are forcing it, right? You are forcing it by multiplying the window function. Now this window function, if you look at it from the frequency perspective, right, what you are exactly doing is you had a h of n. Okay, you had a h of e raised to j omega. Okay, think about this, h of e raised to j omega in the frequency domain. What exactly happens is you had h of e raised to j omega, which was a flat curve, right? Here, this was your curve in the frequency domain, h of e raised to j omega. Okay, now this h of e raised to j omega and w of n is again in the time domain. It is a rectangular pulse, right? It's a pulse, a rectangular pulse, which is it's non-periodic. So 0 to m minus 1. So what happens here is this pulse, a rectangular pulse in the time domain, turns into a sinc function in the frequency domain, right? This turns into a sinc function in the frequency domain. So this is your w of e raised to j omega. This is for the rectangular pulse I am demonstrating. So now if you see the multiplication in the time domain, you are multiplying these two sequences in the time domain. So this naturally will turn into a convolution operation, right, in the frequency domain. So if I do a convolution operation, basically what I am doing is I am taking this particular figure and I am convolving over this particular period from minus pi to pi. So this is what I am doing. So if I start from here from minus pi, and this is your pi, and so this is your rectangular pulse, and this is now my sinc function. So I use this and I do a convolution operation. What will happen is this convolution operation will generate some kind of a pulses, right, some kind of a stop band lobes. So if I do a convolution, if I do a convolution here, I will get at this particular point I will get some kind of this kind of spectrum. So as I move to this particular point, what will happen, or think about like starting from here, and so when I start from here, so when I reach here, so let me just start from this particular point instead, because I am worried about, I'm only concerned about from one side, right? It's symmetric. So think about this one here. So if I start from here and then I move it like this, what I am going to get is something like this. And once I reach here, as I move here, the lobe, this particular main lobe of the window is going to determine my transition band. So if this is wider, then I'm going to superimpose this here, right, for the convolution operation. What is going to turn out is this particular transition band will be still wider. This transition band will be wider. This will depend on the main lobe of the window. So main lobe of the window, main lobe width of this particular window in the frequency domain, or main lobe width is going to determine the main the main lobe in the frequency domain, right? The width of the m is going to determine what is the main lobe going to be. This is pi by m. So if I make it wider, this is naturally going to be like more compressed version, right? So if you expand in the time domain, you basically squeeze in the compress in the frequency domain. So I make this shorter, the main lobe is going to go wider, okay, in the frequency domain. So you will get a bigger transition band, okay. So the transition band is going to go, the slope is going to increase based on the width of the main lobe of the window in the frequency domain, and then you are going to get some kind of a what you call ripples in the stop band too, okay, because it's a convolution operation happening here, right? So you are going to get ripples here. So these are the after effects of doing the truncation, okay, because if you see the convergence doesn't happen here sharply, okay. So that's why you get these ripples.